Now let's consider going over problems involving evaluating limits of trigonometric functions. To succeed in evaluating limits of trigonometric functions, there are some basic facts you have to be familiar with. Also, we will need to review some of the trigonometric identity. So first and foremost, you need to understand that the limit as x approaches 0 of sine x all divided by x is indeed equals to 1. And similarly, the reciprocal of the function still remain unchanged, which implies that the limit as x approaches 0 of x all divided by sine x is still nothing but 1. We can prove this by inspection. So take your calculator and make sure it's in radian because we want to consider very small angles. So what we're going to start with is to start by plugging in values either from the left hand side or from the right hand side. In fact, you can consider the both. So let's consider the both. Let's consider plugging in 0.001 as x and compare the result with negative 0.001. Notice that both these and these are approaching 0. This is approaching 0 from the left hand side, while this is approaching 0 from the right hand side. So we are going to repeat the same process for 0.0001 as that is much more smaller than the previous value, and repeat the same thing for negative 0.001. So let's see what will happen. So starting with 0.001, at the end of the day, the result is still 1. Okay, make sure your calculator is in radian. So what about when it is negative? So let's plug in negative. Notice that the result is still 1 at the end of the day. And now when the value becomes more smaller, when it is positive, the result is still 1. Okay, and when it is negative, the result is still 1. Now notice the pattern that as the value becomes much more smaller as it approaches 0, the result of sine x over x or x over sine x is indeed equals to 1. Now you need to understand that when a constant is multiplying the angle, that is the value of x, the result won't still change. It will still remain 1. Why did I say this? Because regardless of how large that constant might be, as the angle, which is x, as it tends to get much more smaller, then you notice that at the end of the day, the result will still be 1. Let's consider a situation whereby the constant is 100. So what will be a limit as x approaches 0 of sine 100x all divided by 100x? Now at some point in time, if you are plugging in values of x, maybe 0.001, you might not be getting 1. But let's consider a very small value for x. Consider 0.000001. Now if we plug in x as this, notice that at the end of the day, we will still have 1. But let's confirm that. So we are considering sine 100 multiplied by 0.0001. Okay. Then all divided by 100 multiplied by 0.000001. Now notice that at the end of the day, we still have 1. So kindly keep in mind that the limit as x approaches 0 of sine kx all divided by kx, where k is a real number, then the result will always be equals to 1. And that's one of the basic facts you have to be familiar with while dealing with problems involving limit of trigonometric functions. Now, before we go over some examples, let's quickly review some of the trigonometric identity that you have to be familiar with. First, you need to understand that the tan of a particular angle x is indeed equals to the ratio of the sine of that angle to that of the cosine of the angle. Then secondly, you need to understand that the square of the sine of a particular angle plus the square of the cosine of that same angle is indeed equals to 1. With this, you should be able to handle some of the trigonometric function involving limits. Now let's apply what we have discussed so far by going through some practice problems. Example 1. Evaluate the limit as x approaches 0 of sine 3x all divided by 5x. So what should we do in the first place? First thing first, what I would recommend is to find a way to switch this 5, find a way to convert it to 3. So it can be in the form of the limit as x approaches 0 of sine kx all divided by kx, which will end up being 1. So that is our main goal. So to do that, we can multiply both the top and bottom of the function by 3 over 3. Now at this point, we can switch the position of 5 and 3 at the denominator, and therefore we can now have the limit as x approaches 0 of sine 3x all divided by 3x multiplied by 3 all divided by 5. Now since 3 over 5 is a constant, we can bring it to the front of the limit symbol, and therefore we can now have 3 by 5 multiplied by the limit as x approaches 0 of sine 3x all divided by 3x. Since we know that this entire expression will not be nothing but 1, and therefore we have our final answer to be 3 over 5 multiplied by 1, which is indeed equals to 3 over 5. And that is the solution to the first problem. Example 2. Consider the limit as x approaches 0 of sine 5x all divided by x. Now, notice that at this point, we really don't have a constant to be multiplying x, so we can actually introduce it by ourselves. The goal is to make the denominator to be similar as the angle associated with the function, especially the sine function. So we can multiply the top and bottom by 5 over 5. Now we can associate this 5 with the value of x. And now we have the limit as x approaches 0 of sine 5x all divided by 5x multiplied by 5. Since this 5 is a constant, we can bring it to the front of the limit symbol and now have 5 multiplied by the limit as x approaches 0 of sine 5x all divided by 5x. Since this entire expression will be equals to 1, then therefore final answer is 5 times 1, which is indeed equals to 5. And that is the solution to example 2. Number 3. Consider the limit as x approaches 0 of 1 minus cosine x all divided by x. Now, what do you think we can do to evaluate these limits? When you have a situation like this, you have to be very case sensitive. You have to make sure that before we do direct substitution, the denominator must not be 0, as that will lead to an undefined function, and which is what we usually use to avoid in calculus. So the best thing is to find a way to simplify this. Well, what I recommend doing when you have a situation like this is to multiply the whole expression by the conjugate of the numerator. Well, if it is the denominator, in your case, you can always use it. It doesn't mean the goal is just to find a way to simplify the expression. So the conjugate of a trig function is the similar in an expression, but the change in sign of the sign associated with the trig function. What am I saying makes sense? The conjugate of 1 minus cosine x will be 1 plus cosine x. Then I'm multiplying it by the bottom as well. 1 plus cosine x. So this is as if I've not done anything different, because this can cancel out and becomes 1. And 1 multiplied by the whole expression is still the expression. So we are still doing maths. Now let's expand the numerator, but leave the denominator as it is. So therefore, we now have the limit as x approaches 0 of 1 multiplied by 1 is 1. Then 1 multiplied by positive cosine x. So we have plus cos x. The negative cos x times 1, that's negative cos x. The negative cos x times cos x, that's positive cosine squared x. And this is divided by the product of these two. Don't let us expand, let's leave it that way. That's x multiplied by 1 plus cosine x. Now simplifying this forward, we have the limit as x approaches 0 of 1. Notice that positive cos x will get rid of negative cos x, and left over will just be 1 minus cosine squared x, all divided by x multiplied by 1 plus cos x. Okay, bear with me, this is supposed to be negative and not positive, because negative cos x multiplied by positive cos x, the negative times positive is indeed equals to negative. So I'm going to change that now. So we have minus. Perfect. So right now, we can use some of the trigonometric identity we discussed earlier at the beginning of this video. If you could recall, we said that the sum of sine squared x and that of the cosine squared x is equals to 1. So which means if we solve for sine squared x, that is, if we isolate sine squared x, we would have 1 minus cosine squared x by bringing the positive cosine squared x to the side. So which implies that we can definitely replace 1 minus cosine squared x, which is right here, with sine squared x. So that's something you want to understand. So therefore the limit can now imply that we now have the limit as x approaches 0 of sine squared x, all divided by x multiplied by 1 plus cos x. Perfect. Now let me try to get rid of the above expressions so we can have enough space. Now you notice that sine squared x can now be split into sine x multiplied by sine x, then divided by x multiplied by 1 plus cosine x. Now what I would like to do is to break this, because these two looks similar. I can convert them to something I know. So that is why I would need to do that. So I can break the limits and have the limit as x approaches 0 of sine x divided by x, then multiplied by the limit as x approaches 0 of sine x, all divided by 1 plus cosine x. Perfect. I hope you are following the process. So right now, earlier we discussed that expression like this will result in 1. So therefore, I now have 1 to be multiplying the limit as x approaches 0 of sine x all divided by 1 plus cosine x. Now since if we do direct substitution, the denominator would not be 0, then we can go ahead. The cosine of 0 is 1. Then we can have 1 multiplied by sine 0 all divided by 1 plus cos 0. Sine 0 is indeed equals to 0. Then we have 1 plus cos 0 is 1, which is 1 plus 0 over 2, which is 1, okay, times, why did I use plus? Sorry. So which is 1 times 0. At the end of the day, the result is 0. So which means the limit as x approaches 0, let me write it right here, of 1 minus cos x all divided by x is indeed equals to 0. And that is our final answer to this problem. Example 4. Consider the limit as x approaches 0 of sine 7x all divided by sine 3x. By the way, feel free to pause the video and figure this question out yourself. So what do you think we can do in the first place? Well, the goal is to first have the denominator of this sine 7x to be 7x. Then secondly is to find a way to manipulate this sine 3x at the denominator such that it will be having a numerator of 3x. So what can we do? Well, here's what we can do instead. Can we multiply both the top and bottom by 7, 3, and x? These should help us out. But let's see. Now doing this, we can flip the position of some expression. First, I would like to flip the position or switch the position of sine 3x and replace that with 7x. And therefore, we now have the limit as x approaches 0 of sine 7x all divided by 7x, then multiply by the sine 3x. On top of it, I would like to have 3x. So therefore, I can now have 3x all divided by sine 3x. Now this is multiplied by these has been used, these and these has been used. So left over is just 3 at the bottom. So we have 3. Now what about at the top? 3x has been used. Left over is just 7. So we have 7 at the top. Now since this 7 by 3 is a constant, we can bring it to the front of the limit. And therefore we can now have 7 by 3 multiplied by the limit as x approaches 0 of sine 7x all divided by 7x to be multiplied by 3x all divided by sine 3x. Now from the properties of limits, we can distribute the limit to the two expressions. So therefore we can have 7 by 3. So I'm going to put that within parentheses. We can have the limit as x approaches 0 of sine 7x all divided by 7x to be multiplied by the limit as x approaches 0 of 3x all divided by sine 3x. Now, earlier we discussed that any expression like this or this will be nothing but 1. So finally, our answer will be, should I write it here? Okay, 7 by 3 multiplied by 1 multiplied by 1. Therefore, we have 7 by 3 as our final answer. By now, you should have been getting used to the tactics and the approach, and similarly, like and the process of dealing with problems involving limits of trigonometric functions. Let's consider more to aid your understanding in this topic. Now, on to example 5. So feel free to pause the video and figure this out yourself. Consider the limits as x approaches 0 of tan 5x all divided by 3x. Pause the video and figure this out yourself. Now, if you could recall, we said that tan x is equals to the ratio of sine x to that of the cosine x, which means that tan 5x will be the ratio of sine 5x all divided by cosine 5x. So that's a good substitution. We can replace this with this other expression. And therefore, we now have the limit as x approaches 0 of sine 5x all divided by cos 5x. Then the entire expression is divided by 3x. So it seems to be a complex fraction. So instead of using number line division right here, I'll convert it to a regular one. Then we can have the limit as x approaches 0 of sine 5x all divided by cosine 5x, then divided by 3x. Now we can use the concept of keep, change, and flip at this point. Then we can have the limit as x approaches 0. So from that concept, we have to keep the first fraction, which is this, that's sine 5x divided by cosine 5x. Then we have to change the sign to product. Then we have to flip this one. Okay, initially it is 3x over 1. So if we flip it, it becomes 1 over 3x. Then we have 1 over 3x. So therefore, simplifying forward, we have the limit as x approaches 0 of sine 5x all divided by 3x cosine 5x. Now the goal is to make the denominator of this sine 5x to be 5x. We have x already, we only need 5. So let's multiply both the top and bottom by 5 over 5. So now we can switch the position of the cosine 5x, and that was 3, and replace it with 5. How do we grab that? Then we can have the limit as x approaches 0 of sine 5x divided by 5x multiplied by, at the numerator we still have 5. Now the denominator will be left with 3 cos 5x. 3 cos 5x. Okay, now notice that 5 divided by 3 is a constant. So I would like to bring this to the front of the limits. I hope you are following the approach. So therefore, we can have 5 by 3 multiplied by the limit as x approaches 0 of sine 5x divided by 5x, then multiply by 5. Okay, it should not be 1 divided by cos 5x. Perfect. Now we can distribute the limits. We can now have 5 by 3, the limits as x approaches 0 of sine 5x divided by 5x multiplied by the limit. I hope that will occupy what I want to write. Let's see. Let me just squeeze it there. Okay, 1 by cosine 5x. I hope you can visualize that. Okay, fine. Now we have 5 by 3. So this entire expression will becomes 1. Okay, I hope you understand that. Perfect. multiply by, what about this? Cos 5 times 0 is still cos 0. Okay, and cos 0 is 1. 1 divided by 1 is still 1, so that's b times 1. Okay, finally, we have 5 by 3 as our final answer. How do you understand how this is equal to 1? I think I explained it earlier, recently, to say. Well, if you have any question, please feel free to let me know in the comment section below. Now, you should have been getting used to how to deal with problems involving evaluating limits of trigonometric functions. On to example 6. By the way, if you haven't subscribed to this channel, feel free to subscribe to the channel. Also, if you are enjoying this video, feel free to leave a like and thumbs up. Also, comment in the comment section below. So, consider the limit as x is approaching 0 of 9x squared divided by sine squared 4x. Pause the video and figure this out yourself. Well, since both the top and the bottom are perfect squares, can we actually break them in pieces? Let's see. The limit as x approaches 0 implies 3x, which is the root of 9x squared, divided by sine 4x, which is the root of sine squared 4x. Then multiply by 3x again, divided by sine 4x. Notice that the product of these two expressions gives back our initial expression. Now, what should we do at this point? Well, since we are adding values at the top, while three functions at the bottom, the goal is to let this 3 becomes 4. So we can just apply the normal fact that we understand. So, what should we do? Well, all we need to do is to multiply both the top and bottom by 4 over 4, again by 4 over 4. This will help us to switch the position of this 3 and 4, and likewise this. So let's do that. Now we can have the limit as x approaches 0 of, so let's switch the position of this 3 and this 4. So we can have 4x divided by sine 4x multiplied by, now let's repeat the same thing for this 3 and this 4. This has gone already, don't forget. Okay, don't use more than once. So that becomes 4x divided by sine 4x. Now we're having to be multiplying by, this has been increased with 3. It has been switched to 3 over 4 multiplied by, same thing is applied to this. It becomes 3 over 4. Okay. If you are confused, please take your time and digest this properly. What we did is just that we just switch the position of those values, okay, respectively. So now we know that, okay, let me put the limit first. Okay, I don't want to skip any step so you won't get lost. So let's move on. So we have the limit as x approaches 0 of 4x over sine 4x multiplied by 4x over sine 4x, then multiply by 3 times 3, I'm multiplying this, that's 9, and the denominator is 16, as the product is also 16. So 9 by 16. Since it is a constant, we can bring it to the front of the limit, and therefore we can now have 9 over 16 multiplied by the limit as x approaches 0 of 4x all divided by sine 4x multiplied by 4x all divided by sine 4x. Now we can distribute the limits. Distributing the limits, we will have 9 by 16 to be multiplying the limit as x approaches 0 of 4x over sine 4x, then multiplied by the limit as x approaches 0 of 4x over sine 4x. Now, since we know that expression like this will be nothing but 1, and we have 1 times 1. And this whole expression altogether results in 9 by 16. And that is our final answer to example 6. Now, on to example 7. Before we proceed to example 7, let's try to review more trigonometric identity, as we will be making use of them along the way. So, it is important to understand that the sine of 2x is equal to 2 sine x cosine x. Similarly, the cosine of 2x is equal to cosine squared x minus sine squared x. In trigonometric, we call this identity double angle formants. So please make sure you keep that in mind. Now let's try to review the reciprocal function of the functions. I hope you had that, okay? The reciprocal of cosine function x is equal to secant function x, while the reciprocal of sine function x is equal to the cosecant, which is written for short as CSCX, and the reciprocal of tan function x is equal to the cotangent, written as cos for short x. Now, since tan x is equal to sine x over cos x, then the reciprocal of this is just the flip in position of the expression involved, which implies that cos x is cos x over sine x. Please write this down or put them somewhere at the back of your mind or at your left hand, as they will be very, very much helpful. So now let's proceed to example 7. So consider the limit as x approaches 0 of cos 2x minus 1 all divided by cos x minus 1. So pause the video and figure this out yourself. Then, after getting the solution, unpause it to see if you got it right. So let's begin. First, let's replace cos 2x with some manipulation expressions. Let's see. Since we said earlier that cos 2x is indeed equals to the square of cos x minus sine squared x. Well, notice that from the first three identity we discussed, we said sine squared x plus cos squared x is equal to 1. So which implies that sine squared x is equal to 1 minus cos squared x. So what I would like to do is to replace sine squared x with this expression right here. Therefore, okay, let me consider this like that. We can now have cos 2x to be equals to cosine squared x minus, now we said 1 minus cosine squared x. Now simplifying the right hand side, we have cosine squared x minus 1 distributed the negative plus cosine squared x. And these are like terms. Adding them up, we have 2 cosine squared x minus 1. Okay, perfect. Now, what I would like to do is to go back to the expression given. So I will replace cosine 2x with 2 cosine squared x minus 1, since they are equal. I hope you got that. So therefore, we can now have this. We now have the limit as x approaches 0 of 2 cosine squared x minus 1, then the other minus 1 minus 1. Okay, please don't get me wrong. This is the same as cosine 2x. This minus 1 is left aside, so which is it right here. Okay, perfect. So therefore, we can now divide that with cosine x minus 1. Now, minus 1 is minus 2. So we can now have the limit as x approaches 0 of 2 cosine squared x minus 2 all divided by cosine x minus 1. Now, since 2 is common, I can factor it out and have the limit as x approaches 0 of 2 in bracket cosine squared x minus 1. And this is divided by cosine x minus 1. Now, from our knowledge in algebra, the difference of two squares is equal to their sum multiplied by their difference. Okay, perfect. That will be a minus b, a plus b. Good. So therefore, we can now have the limit as x approaches 0 of 2, since these are two squares, and we have a difference in between them. We can now have it to be cosine x minus 1 and multiply by cosine x plus 1. Then this is divided by cosine x minus 1. Now notice that at this point, cosine x minus 1 can cancel out. Then we can have the limit as x approaches 0 of 2 multiplied by cosine x plus 1. Now since 2 is a constant, it can come to the front of the limit, and therefore we can now have 2 multiplied by the limit as x approaches 0 of cosine x plus 1. Now, since if we do direct substitution, we won't have an undefined function. So definitely we can go ahead and plug in 0 as x into the function. So we can have a half 2 multiplied by cosine 0 plus 1. So cosine 0 is 1 plus 1. So we have 2 times 2, which is indeed equals to 4. And that is our final answer to this problem. One good thing I can recommend is that if you have the privilege to have access to a calculator, you can always use it to confirm the solution, if you are right or not. And that is the solution to example 7. Now on to example 8. So consider the limit as x approaches 0 of the function at 0 called 2x minus cosecant 2x, then all divided by x. Feel free to pause the video and figure this out. So, first thing first, can we replace the inverse function or the reciprocal function with the equivalent first three functions? So let's see. We have the limit as x approaches 0. We said cot 2x is the ratio of cosine 2x over or to sine 2x. So that will be cos 2x by sine 2x minus, we said cosecant 2x is the reciprocal of sine x. So that will be 1 by sine 2x. And it's entirely divided by x. So let's deal with the numerator. Let's combine it to a single fraction. Since 2x is common, this can turn out to be the LCM. So we have the limit as x is approaching 0 of, okay, sine 2x is the LCM. So what will now be the numerator? Well, since they are like the LCM, the numerator will just be the difference between what we have seen or we have seen. So that will be cosine 2x minus 1. Okay, for those who are wondering, what we are going to do is to set that sine 2x in sine 2x, that is just 1. And we are going to multiply it with its numerator, which is this, which will give us back cos 2x. Also, sine 2x in sine 2x will gives us 1. And if we multiply that by 1, we still have 1 back. Then plug in the sign connecting them in between. Then you have it back. So the long division, let's convert it to a regular. So simplifying forward, limits as x approaches 0 of cosine 2x minus 1 divided by sine 2x. Okay, let's just multiply that, multiply by 1 by x. Okay, I've used the concept, keep change and flip. So I keep this one and just flip x over 1 becomes 1 by x. And then simplifying this forward, we have the limit as x approaches 0 of cosine 2x minus 1 and all divided by x sine 2x. Now, since the denominator is in terms of sine 2x, so let's find a way to manipulate this numerator to be in form of sine function. So what should we do? Well, let's go back to our three identities. That is why I said those identities are very, very important. Why the language problems involving limits of trigonometric functions. Earlier we said that cosine 2x is equal to cosine squared x minus sine squared x. Now, we also said that sine squared x plus cosine squared x is equal to 1. What if we solve for cosine squared x? Well, isolating cosine squared x, we have it to be equal to 1 minus sine squared x. And what we're going to do next is to replace cosine squared x right here with 1 minus sine squared x. And therefore, we have cosine 2x to now be equal to 1 minus sine squared x minus sine squared x. This one is for the cosine squared x, while this one is still there. So therefore, simplifying forward, we have cosine 2x to now be equals to 1, these are like terms, minus 2 sine squared x. Perfect. Now, isolating 2 sine 2x or 2 sine squared x to say, well, let's just bring it to the side, okay? So that will just be 2 sine squared x equals, this will come to the side. So that will be 1 minus cos 2x. 1 minus cos 2x doesn't really look like what we have right here. But we can actually make them the same. How? Well, what if we factor out negative sign right here? Notice that our leftover result will correspond to what we're seeing right here. But let's see. If we have cos 2x minus 1, then we factor out negative sign. Factoring out negative sign, this cos 2x will carry negative sign. Negative cos 2x. because when the negative sign expanded, it should convert back to positive. Now this one will now carry positive sign plus 1, which can become negative 1 minus cos 2x. So you can clearly see that what we're having here right now as correlates to what we're having here. So what I would like to do is that I won't just replace cos 2x with negative bracket of 1 minus cos 2x, but I will entirely replace 1 minus cos 2x with 2 sine squared x. I hope you didn't get lost. Okay, let me do it one after the other. Okay, since this is equal to this, so let's replace it. So this expression, let's say, can become the limit as x approaches 0. So cos 2x minus 1, we said is the same as negative 1 minus cos 2x. So I will write negative 1 minus cos 2x instead. Then I will divide that with x sine 2x. Now I said 1 minus cos 2x, or we showed it out, is equals to 2 sine squared x. So we can replace 1 minus cos 2x with 2 sine squared x, and therefore we now have the limit as x approaches 0 of negative 2 sine squared x divided by x sine 2x. Perfect. Okay, let me get enough space. Oops. Now also, if we recall, we said that sine 2x is equal to 2 sine x cos x. So can we just replace this sine 2x with this? We can do that actually. So we can now have the limit as x approaches 0 of negative 2 sine squared x, then all divided by x multiplied by 2 sine x cos x. Now sine x reduces sine squared x to the limit as x approaches 0 of negative 2 sine x. We now have only 1 sine x left, divided by, and this becomes 2x cos x. This sine x part is gone. 2x cos x. Perfect. Now the 2's cancels out, and the minus can come to the front. Then we have minus the limit as x approaches 0 of sine x over x cos x. So let's break the limits to keep things straightforward. So now we can have negative the limit as x approaches 0. So what I will do is that I will just detach this from cosine x because I can do something about that. Sine x over x, then multiply by the limit as x approaches 0 of 1 over cos x. Perfect. Now we have negative, this entirely becomes 1. 1 times, well, from direct substitution, cosine 0 is 1, and 1 divided by 1 is 1. So at the end of the day, the result is nothing but 1. And that is the final answer to this problem as well. So which implies that the limit as x approaches 0 of cos 2x minus CSC2x all divided by x is nothing but negative 1. So that is it to this problem. On to example 9. So please, I would recommend to kindly please pause the video and figure this out yourself. Apply the knowledge you have learned right from the beginning of this video, everything you have learned so far, and do it with your whole hand as well. So consider the limit as x approaches 0 of sine squared 7x plus 3 tan squared 3x, then all divided by 8x squared. Okay, pause the video and figure this out yourself. So now, if you want, you can convert tan squared 3x to sine squared 3x over cos squared 3x. But I won't do that right now. Instead, I would split 8x to sine squared 7x and that of tan 3 tan squared 3x. So let's see. In fact, I will distribute the limit straightforward. So let's have the limit as x approaches 0 of sine squared 7x all divided by 8x squared plus the limit as x approaches 0 of 3 tan squared 3x all divided by 8x squared. Okay, we're still doing math. All we have done is that we just try to split the fraction, okay, and the limit. Now we can focus more on this. First, let's split sine squared 7x into 2. So we have the limit as x approaches 0 of sine 7x multiplied by sine 7x and all divided by 8x squared plus the limit as x approaches 0 of 3 tan squared 3x all divided by 8x squared. I actually want to get this part simplified first before focusing on the other part, so as to avoid rough work, you understand, as we don't have enough space. So now, let me consider themselves. So I have enough space. Simplifying forward, let me just put it like that. Let me just adjust it a little bit below. Okay, so I'll be using letter. So we have the limit as x approaches 0. Now, we want to make the denominator of each of the sine 7x to be 7x. So we can apply our postulate, okay, or the fact we learned at the beginning of the video. So that will just be sine 7x multiplied by sine 7x and all divided by 8x squared. Now, since we want to use 7, we can use 7 times 7 all divided by 7 times 7. You know, we are making use of 2 7s. That's why we are multiplying by 7 times 7. So we have the limit as x approaches 0 of sine 7x. So let me put this one first, divided by. So I will take 1 7 and 1 x from the x squared. So we have 7x. Then this is multiplied by sine 7x divided by take the other 7 and take the other 1 and the other x squared. So we have 7x. Then multiply by these 2 7s are still there. So that's 49 divided by leftover at the denominator is 8 divided by 8. So this is a constant. You can take to the front. So we have 49 over 8. Okay, then put it in brackets. So we put the limit as x approaches 0 of sine 7x all divided by 7x, then multiply by the limit as x approaches 0 of sine 7x all divided by 7x. Perfect. So now, well, I can't get to that for now. I'm still using it. Okay, or this can go. So therefore, we now have 49 over 8 Well, since these two expressions becomes 1, so that will be 1 times 1, which will be 49 over 8. Oops, I got 49 over 9. So that is our final answer to this entire part. So now I can get rid of it and put 49 over 8. So this part is 49 over 8. So now let's focus on this. Very good. So we want to evaluate the limit as x approaches 0 of 3 tan squared 3x all divided by 8x squared. So we know that tan squared 3x is the same as sine squared 3x divided by cosine squared 3x, and then we have to be divided by 8x squared. Okay, so this becomes a limit as x approaches 0 of 3 sine squared 3x divided by cosine squared 3x multiplied by 1 over 8x squared. I hope you're following. Okay, I've just used the concepts we have been using earlier so far. You understand? So this implies that the limit as x approaches 0 of 3 sine squared 3x and divided by 8x squared cosine squared 3x. Now, just like before, first let's take the 3 outside and the 8 outside or to the front of the limit. They are constants, so they can definitely come to the front of the limit. So therefore we can have the limit. Okay, let me put it to the front first. We can now have 3 over 8, the limit as x approaches 0 of sine squared 3x divided by x squared cosine squared 3x. Okay, now this implies 3 over 8, the limit as x approaches 0. So let's split the sine squared 3x just like before. So we have sine 3x multiplied by sine 3x and divided by x squared cosine squared 3x. So now the goal is to have the denominators to be 3x, so we can apply the fact we have left. So therefore, we now have 3 over 8, the limit as x approaches 0 of sine 3x multiplied by sine 3x divided by x squared cosine squared x. Okay, cosine squared 3x multiplied by, since we want to make use of 3 and we have up to 2x, x squared, I just use 3 times 3 over 3 times 3. Okay, now we have 3 over 8, the limit as x approaches 0 of sine 3x. Okay, so I'm breaking this right away, divided by selecting 1 3 and 1 x. So we have 3x multiplied by sine 3x divided by selecting the other 3 and the other x. That's 3x multiplied by, left over at the numerator is 9. So multiply by 9, that's 3 times 3. And at the denominator is cosine squared 3x. So we have cosine squared 3x. Incredible. So now let's move on. So okay, this is 4 Don't mess it up. Let me write it. Okay, it's 449. Very good. Now we have 3 over 8 multiplied by, so the 9 is constant. Actually want to bring it to the front of the limit as well. You understand? So multiply by 9 and multiply by the limit as x approaches 0 of sine 3x divided by 3x, then multiply by sine 3x divided by 3x, multiply by 1 over cosine squared 3x. So now we can distribute the limit as well. So we can just have our final answer. So we have 9 times 3, that's 27. 27 over 8. Then in the big bracket, the limit as x approaches 0 of sine 3x over 3x multiplied by the limit as x approaches 0 of sine 3x over 3x, then multiplied by the limit as x approaches 0 of 1 divided by cosine squared 3x. So simplifying this forward, we have 27 over 8. This entirely becomes 1. Multiplied by this also becomes 1. Multiplied by, will this become 1? Ask yourself. Yes, it should be 1. Okay. The cosine squared of 0 is still cosine 0, which is still 1. And 1 divided by 1 is still 1. Okay. So finally, we have 27 divided by 8 multiplied by 1, which is 27 over 1. Actually, 27 over 8. So this expression becomes 27 over 8. So we can get rid of it and put 27 over 8. And if you add them up, 8 is common as the LCM. So what is the sum of 27 and 8? So we have 49 and 27. Did I just say 27 and 8? Sorry, I actually want to say 49 and 27. So the sum of 49 and 27, the 4 and 2 is 6, 9 and 7 is 16. So that's 76. So we have 76 over 8. And 8 going to 76? No, not really. But we can break it in pieces. 76 divided by 2, that gives 38. While 2 in 8 gives 4. 2 can still work. 2 in 38, that gives 19. While 2 in 4 gives 2. So this is our final answer to the problem. And this is the solution to example 9. By now, it should have been used to solving problems involving limits of trigonometric function. I hope you find this content helpful, and I hope by now you should be able to do and deal with problems involving limits of trigonometric function. If you haven't subscribed, like I said, do what subscribe. Thanks for watching. See you guys in the next video. If you have any question, feel free to let me know in the comment section below. Thank you one more time. However, here's an exercise I have for you. Feel free to share a solution with me in the comment section below. So consider evaluate the limit as x approaches 0 of tan x minus sine x all divided by x to the power of 3. Let me know your solution in the comment section below. Thanks for watching. Bye for now.